All right, we're taking a look at inverse trig functions, specifically differentiation, and these are the notes for section 5.6 on that particular topic. And I'm looking at the sine curve right here. I think I have it written here. I'll drag it down. And you can take a look at the sine curve. It itself is a function. It passes the vertical line test, but its inverse is not a function because it does not pass the horizontal line test. This function doesn't anyway. So what we do is we limit. I'm going to go here and put a point right here at pi over 2 and 1. Try to do that very carefully. And then another one here at pi over 2, 1. I think I meant negative pi over 2, negative 1 last time I mentioned that. And this portion from here to here, from these 2 points in between, if I restrict that in this portion right here that I'm highlighting, that part of the inverse is a function. And if I take a look at what that looks like, I have that graph, so I'm going to not save this. And right here is the inverse. And what happens is the range and the domain interchange. So these values right here, if I highlight this, and I think I can do that. Maybe that doesn't do that. Well, anyway, this point is negative 1 comma 0, and this point is 1 comma 0. So now that's my domain. And this value up here is pi over 2, so this point is 1 comma pi over 2, and my y values are now my angle measurements, and in here are my ratios, and this point right here is a negative 1, negative pi over 2. And so you can see it stops right here, and within this restricted area, because as I would go further down, what would happen is this sine inverse would start coming back this way, and it would no longer be a function. But within this interval of negative 1 to 1, I have a function. And so we can do the same thing with sine and cosine. I'll get a new sketch here. I'll show you what I mean by that. And I'm going to graph cosine. And this is what, I'll make this a little bit bigger and make this a little bit. So this part right here, from here to down here, from 0 to pi, that portion of the cosine function, its inverse would be a function. And I'm going to take a look. I'm going to make a new sketch here. And I'm going to show you what that looks like. I'm going to graph the inverse. And you can see this is going from, let me make this a little bit bigger. Right here, this is negative 1 to 1 again. And this is going from 0 to pi. And so that's what the arc cosine looks like. And I'm going to make another one. Since I can make multiple sketches, I will. Here's the tangent. And you can see it's repetitive and it has asymptotes here at pi over 2 and at negative pi over 2. So if my domain is restricted right here, its inverse will be a function. Now when I graph that, again this is the tangent right here. I graph the arctangent. Here's the arctangent right here. And you can see it's going from its domain, its range is going from negative pi over 2 to pi over 2, and its domain goes from negative infinity as I'm going to the left to positive infinity as I'm going to the right. And so if I take a look at that, right here I would have a horizontal asymptote at pi over 2, and I would have horizontal asymptote at a negative pi over 2. And that part of the inverse would be a function. And I continue to talk about those. If you take a look, there's a listing on them on page 380 that gives you the domain and ranges of the entire trig inverses, and it would be worth your while to take a look at them. Alright, I'm going to do a few of the examples about this on this particular video. So I'm going to quit Sketchpad here. And I'm going to get something to draw on. And so here's example 1. And example 1 says I have something like this. Y equals the arc sine of a negative 1. So there's my ratio. And it wants you to figure out what y is. So that means the sine of y would equal a negative 1/2. Well, if I take a look, and what I'm going to have here is I'm going to have a portion of the unit circle. Well, the portion of the unit circle I'm going to show is this portion right here, because the portion of the unit circle from this point right here, 0, 1, and 0, negative 1, means I've gone from pi over 2 radians to a negative pi over 2 radians. Those are in the first and fourth quadrant. And so this is where y is positive in the first quadrant, y is negative in the second quadrant. Well, if I take a look, there are some important points right here. What I can, in the first quadrant, I call 1, 2, 3, 4, 5 points. This point right here is 1, 0. This point right here is square root of 3 over 2, 1/2. This point right here is square root 2 over 2. And this point right here is 1/2 square root of 3 over 2. Now, these are the only points that I remember these right here, because when I reflect these, right here, I'm going to have the square root of 3 over 2, comma, negative 1/2. And so what's my angle measurement right there? Well, my angle measurement right here, my y value, is equal to 30 degrees, or what is considered pi over 6 radians. So my negative 1/2, which is my y value, which is the sine of y, is going to be, y is going to be a negative pi over 6, or what is commonly known as a negative 30 degrees. Alright, let's take a look at the next example. Example 2, we're looking at y equals the cosine of 0. Well, now if I take a look at cosine of 0, here's my unit circle again. This point is negative 1, 0. This point is 1, 0. And this point right here is 0, 1. And the reason I choose this is because cosine inverse excuse me, I need to rewrite this right here. This is, I wrote this wrong. Y equals the arc cosine of 0. So I'm saying the cosine of y equals 0. What angle measurement? Well, when you have these ordered pairs, this is your cosine value. This is your sine value. Okay, so the first part of the ordered pair is cosine, the second part is sine. Well, if you notice right over here, this is where the cosine of y equals 0. Well, how many radians did I have to turn to get up to here? Well, I went 90 degrees, which is the same as pi over 2 radians. So y in this case is pi over 2, and that's my answer. All right. Let's try another one. Let's look at example 3. This one's more general. Excuse me. We're going on to tangent here, so I have y equals, this is number 3, the arc tangent of the square root of 3. Well, I'm thinking the tangent of y is equal to square root of 3. And a lot of times I can't remember that, but I do know that the sine of y over the cosine of y is equal to the tangent of y. So that means the sine of y over the cosine of y has to simplify down to the square root of 3. Over here I could have the square root of 3 over 2, and cosine is 1/2, because those are my only choices. Either when the sine is 1/2, the cosine is the square root of 3 over 2. If the sine is the square root of 3 over 2, then the cosine is 1/2. And if I take a look at this, I know that the square root of 3 over 2 divided by 1/2 is equal to the square root of 3. So when is the sine of y equal to square root of 3 over 2? That question is equivalent to asking when the tangent of y is equal to square root of 3. Well, we figured out on a previous problem that the sine of y equals the square root of 3 over 2 at pi over 6. So our only other choice is when y is equal to pi over 3, or what is commonly known as 60 degrees. Okay, next problem. Number 4. Okay, if we're going to use our calculator to figure out y equals the arc sine of 0.3. So I'm going to go to my calculator, which is right here. And you got to make sure you're in radians. And so I'm going to go, let's execute there. And I'm going to go sine inverse of 0.3. Execute. And there's my answer right here. It is 0.305 is the approximate answer. All right, problem number 5. Let's say I have the arc tangent of 2x minus 3 is equal to pi over 4. Well, what does that mean? That means the tangent of pi over 4 is equal to 2x minus 3. So we need to know the tangent of pi over 4. Well, it is 1. It's the square root of 2 over 2 over the square root of 2 over 2, which is the sine of 45 degrees, or the sine of pi over 4 over the cosine of 45 degrees, or the cosine of pi over 4. So anyway, I get 1. I let 2x minus 3 equal 1. That means 4 is equal to 2x. That means that 2 is equal to x. And there's my solution. Example 6 are examples that we're going to use probably to set up our proofs that we're headed towards. And so I'm going to clear this. In example 6, this is the method I'm going to use. I'm given that y equals the arc sine of x. And I'm asked, well, what then is the cosine of y? What can it be? Well, what I do is I do this method. I take and I rewrite this expression as the sine of y equals x. And then I draw a picture to see what that represents. Well, sine of x, or excuse me, the sine of y is the same as opposite over hypotenuse. Well, this is the same as x over 1, so x is my side opposite and 1 is my hypotenuse. And then using the Pythagorean theorem, which would mean that a squared plus b squared is equal to c squared, and so I'd have a squared plus x squared is equal to 1 squared, or 1, and a squared would equal 1 minus x squared, and that would mean a is equal to, and I'm going to choose a positive square root of 1 minus x squared since I'm talking about a length. That's this distance right here, 1 minus x squared. So what's the cosine? Well, the cosine of y is adjacent over hypotenuse. So in this case, it's going to be the square root of 1 minus x squared all over 1, which is simply the square root of 1 minus x squared. Number 7 is similar to that, except I'm given a number in this case. I'm given that y equals the arc secant of the square root of 5 over 2. What would the tangent of y be? Well, that means I'm going to go make my triangle. Here's y, and it's a right triangle, and the secant of y, well, the cosine of y, you can remember, is adjacent over hypotenuse, so the secant must be hypotenuse over adjacent. That means the square root of 5 must be my hypotenuse, and my adjacent must be that 2. Now to figure out this side, again, it's going to be the square root of c squared, which is 5, minus a squared, which is 4. And so I'm going to get the square root of 1, which means this is equal to 1. So the tangent now is opposite over adjacent. So in this case, my opposite is 1 over 2. It's this ratio over that. Excuse me, it's that value over 2. Alright, so those are some practices of using right triangle trig to come up with some values.